We have two types of projectile motion questions that we can see in Physics 20. There is the one that is launched off of the edge of the building or a cliff that looks like this. And there's the one that's launched from ground level at an angle like this. Now, you can imagine we could conceivably also see one where it's launched at an angle from the top of the building, or maybe it's launched from an angle and it lands on the top of a building. We won't see that in Physics 20 because that would require this equation called the Quadratic Equation, which some of you have never even heard of, let alone mastered. So we won't see those. We'll see just these two questions. Now, with these two questions, we always set it up the same way, no matter what. This is question number 1 on your final exam, and you can be pretty sure that you're going to get one or both of these on your unit test on Monday. We did it on your unit assignment, right? We get both of them on our unit assignment. You're going to get one or both of them on your unit test on Tuesday, not Monday. What do you do to start off? Once we have our picture drawn with all our givens written, which we don't really have a question here, so there's no givens to write down on there, what do we do? What do we write down next, Emily? Yeah, write down your formulas. So for our x and y components, we have two formulas, two equations. What equation do we use to describe the x component? Yep, Marcus? Good. We use v is equal to delta d over delta t for both of them, Marcus? No, even for both problems, a left and right problem? Yes. V is equal to delta d over delta t for the x component for both problems. Okay, reason is, horizontally, the velocity isn't changing. There's no reason for it to speed up or slow down horizontally. Forces cause something to speed up or slow down. There's only one force acting here, and that's gravity acting down. So if it's going to speed up or slow down, it's going to be downward on the vertical axis, not on the horizontal axis. So our group A equation applies most definitely here. Now, on our y component here, that's a group B problem, right? We're allowed to use any of those group B problems, any of those group B equations, but there's one that generally works for us. And the reason it generally works for us is because it's the equation for a parabola, and that's the shape of this path. What is that equation that we're going to use here, Martin? Good. D is equal to VIT plus 1/2 AT squared. And we're going to do that for both of these. Doesn't matter whether we've got launched at an angle or launched horizontally off the top of a building. Doesn't make any difference. We start off the same way. Now, for the most part, these two questions are the same, but there are three fundamental differences between these two questions. I'm going to write down some numbers here just so that we can distinguish those differences here. Let's say the velocity here is 10 meters per second, and the height of this building is 20 meters. This is launched at 10 meters per second at an angle of 30 degrees. The first difference that we have is the horizontal velocity. What's the horizontal velocity in the first one? 10 meters per second. It's just a number that's given to us, 10 meters per second. What's the horizontal velocity in the second one? We don't know right now, do we? Why don't we know? Well, because we have a funny angle, and I don't like funny angles. So we have to take that funny angle off to the side, get rid of it, and then figure out what the x component is of that initial velocity. 10 meters per second, okay, this is going to be x, this is going to be y. And of course our angle is 30 degrees. Our x component can be found by the cosine function, works out to be 8.66, and the y component can be found by the sine function, works out to be 5.0. We box it off because that's what we do. No good reason, that's just what we do. We box it off. Now, what would we say the x component of this velocity is? This 10 meters per second, this 10 meters per second that is erased from the family picture, that is dead to us now? Yep, 8.66. Right, we're not going to use 10 because it's gone forever. As far as we're concerned in this question, it's 8.66. So there's the first difference between these two problems. Now, the second difference between these two problems is the vertical displacement. The vertical displacement in the first problem is what? What is it? negative 20. Now, sometimes it might be like negative 50 or negative whatever, right? Sometimes we might not even have the number, but it's different than it is in the second problem for sure. Okay, in this case, we'd say negative 20. Don't forget that negative, because it is down from where it started, right below where it started. What's the y displacement in the second problem? 0. Now, in some of these problems, like down the road, if you take physics in university, and it's launched off the top of a building, that vertical displacement might be negative something there as well, right? But for now, for us in Physics 20, it's always going to be 0 when it's launched at an angle because it ends at the same level as it started. So we'll make it 0. Good. And finally, what's the third? What's the third difference? That would be VI, right? The y component initial velocity. What's the initial velocity of the y component in the first problem? How much of that 10 meters per second is up and down? Scott? 0. And how much of this 10 meters per second in the second problem is up and down? 5, right? It's 10 sine 30 degrees. It's going to be 5.0 meters per second. Now, the rearranging of it becomes a little bit tricky sometimes, especially solving for t in the second equation. Okay, but in the end, we're set up now, and now it's just a matter of, it is just a matter literally of subbing in numbers and solving for something, anything, and then using that anything to get what you're actually looking for. One more thing here before I set you free. If I'm looking for the maximum height, and we are asked maximum height sometimes, quite often actually, especially when we've got one of those problems where it's launched at an angle like the second problem that we see here. When we're asked for maximum height, there's a number of things that we could do, but there's one thing that we typically do. In the first problem, easy. There's nothing to do, right? What's the maximum height in the first problem? 20 meters. If it goes straight off a 20-meter building, the maximum height is 20 meters. There's nothing to do there. Probably won't be asked that question. But in the second question over here, you might be asked for the maximum height. If that's the case, you're going to do the y component. You're going to do the y component and then use VF squared is equal to VI squared plus 2AD. What would VF be? If you're trying to find the displacement at the top right here, what would VF for the y component be at the top? 0, right? And VI would be 5, and A would be negative 9.81, and you'd be solving for the displacement. The displacement, when VF is 0, is the maximum height. You just rearrange and solve for delta D. All right, I'm going to set you free here right now on your worksheets. Your worksheet number, on worksheet number 9, questions 6 and 7. A reminder, question number 7, we're looking for the maximum height. That's what we just looked at, right? The maximum height. Question number 6, we're looking for the height of the ball at 0.8 seconds. Not the maximum height, but at 0.80 seconds. I'm going to leave that for you to see if you can figure that one out yourself. Okay, it's not crazy hard. Okay, don't overanalyze it. But give it some thought and see what you can do with it. Let's have a look now at question number 6. It says a ball is thrown from height of 2 meters, angle of 60 degrees, speed of 10 meters per second, caught by another person at a height of 2 meters. The nice thing about this one is that it's caught at the same height that it was thrown at, which means that it's like it's going from ground level to ground level. It doesn't matter. The 2 meters doesn't matter, right? The vertical displacement is still 0 since it ends up in the same vertical position. So let's draw this. I'll just draw it as if it's going from ground level to ground level. Looks like this. What's the shape of that path? Parabola. 10 meters per second. We got an angle of 60 degrees here. We know we're going to have to take that 10 meters per second off to the side and get rid of it. So let's do that right now. Okay, this is our x component right here. And this is our y component right here. And our angle, of course, is 60 degrees. So we're going to find the x component using the cosine function, because the cosine function gives us adjacent over hypotenuse, and that's what x is, the adjacent side. Cosine 60 degrees is equal to x over 10. I think that works out to be 5.0, doesn't it? And then we're going to say sine 60 degrees is equal to y over 10. That's opposite over 10. the y component ends up being equal to 8.6602 meters per second. Now we're going to box that off because that's what we do. And now we're going to go over and do our thing with the x and y components of this parabola. X component, y component. What equation do we use to describe, Jordan, the x component of it? Yep, because it's a group A problem that travels at a constant velocity horizontally. So Anna, what one do we use to describe the y component? Good. VIT plus 1/2 AT squared. Good. Now we start subbing numbers in. Whatever numbers we got, sub them in. Just sub them into the right place, right? Do we know what the V is for the x component? Hannah, do we know what V is for the x component? What is it? 5 meters per second. Good. So let's sub that in, 5 meters per second. Do we know what the horizontal displacement is? Do we know what delta D is for this left side? Blake, do we know what that is? Delta D right here? No, we don't. That's right. We don't know what time is yet either, right? So that doesn't seem to have helped me a whole lot, but you know that in all likelihood, we're going to come back to this, right? And it is going to help me. Okay, let's go to the y component then. Do we know, John, do we know what the y component of the displacement is? What this value of this is? It's 0. Starts at 2 meters, ends at 2 meters, so it's 0, the displacement. VI for the y component. Trent, do we know what that one is? Good, 8.6602 meters per second. Times the time plus 1/2 of neg 9.81 times the time squared. Now this is what bugs people is solving for t here. It's a lot easier than solving for t if d wasn't 0. Because if d wasn't 0, we'd need that quadratic equation, right? Which some of you don't even know what it is yet. Although next semester when you take math, and you get taught the quadratic equation, you're going to be like, that's what he was talking about, the quadratic equation. All right, so let's divide every term by t. 0 divided by t, t divided by t, t squared divided by t. What happens here? 0 divided by t is 0. T divided by t is 1, so it becomes just 8.6602 times 1. Half times neg 9.81 is neg 4.905. T squared divided by t. T squared divided by t is what? T, right? It's, take the square off and the t on the bottom, 4.905 t. Now the easiest way I think to do this is to take this term over to the other side by adding. So we get 4.905 times t equals 8.6602. Divide 8.66 divided by 4.905. What does that give us? What does it give us? Quick. Somebody's got that for time? 1 point what? 765 seconds, which would round to 1 point. How many digits should we have here? 2 digits. 1.8 seconds. Yeah, that's the final answer for A. But we're going to take the unrounded number, plug it in here. 5.0 is equal to delta D over 1.765. We solve for delta D, and it works out to be, what is that? Hold on for a sec. Let me see if I can do this. 8.825 meters, which is going to round to 8.8 meters. Good? Now we're looking for the height of the ball at 0.8 seconds. Some of you had trouble with this. We didn't do an example like that where we're finding the height of the ball at a particular time. How do you do it? You want to find the height of the ball, which component do you do, an X or Y? Y component, right? You want to find the height, what variable you're solving for? D, delta D, the displacement. You got the time. Why don't we just do this in the Y component? Delta D is equal to VIT plus 1/2 AT squared. Wait a sec, isn't that what we already did? Yeah, it's what we already did when time was 1.76 seconds. Let's find delta D when time was it 0.8? 0.8? Let's solve this time for delta D instead of delta T, when T is 0.8. Let's use our calculator for this one. Let's say 8.6602 times 0.8. Let's press enter. Let's add that to 0.5 times negative 9.81 times 0.8 squared. Gives me a value of 3.8. 3.8 meters, is that good? How many people got that? Good.